So this will finish up to 4. I'm afraid it's going to go into a part 3 because it just feels so thick, the amount of work that I need to do. Let's do this first derivative. It's a simple e. If I want to think of the coefficient, it's really 1 times e to the 7x. And to do the derivative of an e that has a coefficient that doesn't have a letter, it's the coefficient times the derivative of the exponent, and then times the e function with the same exponent. The derivative of the exponent, the derivative of 7x is just 7. So this is going to be the coefficient 1, which I really don't need to write, times the derivative of 7x, which is 7, times e to the 7x. So the derivative here is just going to be 7e to the 7x. So they're real easy. And I believe that you can go from the problem to the answer without showing any work. If you feel comfortable, do it. Let me not put the coefficient of 1 in. It seems not necessary. I'm just assuming it's there. So I'm just going to go straight now to the derivative is the derivative of the exponent without showing the coefficient of 1. I could slide that 1 behind there, but why? Because it's just going to go away anyways. It's the derivative of the exponent times the e function unchanged. Well, the derivative of 9x is 9. The derivative of minus 1 is 0, so the derivative of the exponent is just 9. And the e function doesn't change when we're doing e derivatives. So in problem 4, the derivative is 9 times e to the 9x minus 1. We don't subtract 1 from the exponent when we're doing e derivatives. For number 6, again, because the coefficient's an implied 1, I don't need to write the coefficient down. I'm going to say the derivative is the derivative of the exponent, in this case the variable's t, so I'm going to say d dt, and you shouldn't write this down, just do this in your head. I'm just emphasizing this is what I'm doing. I'm taking the derivative of the exponent, and that's the proper symbolism to say that I'm taking the derivative of the exponent, times the e function, not doing anything to the exponent. Here, this derivative is a binomial, so the derivative of the exponent is going to need to be thrown in a parentheses. Normally, when I take the derivative of the exponent, it's a monomial, so I don't have a parentheses that I include in my answer. But here, the derivative of 7t squared is 14t. The derivative of minus 3t is minus 3. The derivative of 1 is 0. Just because the derivative of the exponent's a binomial, I'd leave that in my answer in a parentheses. This is the answer. There's nothing more I could do to simplify it. Problems 7 and 8 have that coefficient, which is fine. So the derivative for number 8 is my coefficient times the derivative of the exponent times the e function unchanged. That's going to give me 8. And then the derivative of 2x is 2. The derivative of 5 is 0. So the derivative of the exponent is just 2. I'm going to multiply the coefficient of 8 times the derivative of the exponent and get 16. And then the rest of my answer is going to have the e unchanged. Now kicks it up a notch because preceding the e, I have a coefficient with an x. Now I need to do the product rule. So I'm going to have my first factor, which is 3x to the 4th. My second or my last factor, which is e to the x. I'm setting up for the product rule because there's multiplication and both factors have an x. I'll take the derivative of 3x to the 4th and get 12x cubed. And for the derivative of e to the x, if I want to do the derivative of e to the x, the coefficient is 1. I won't worry about it. I'm going to take the derivative of the exponent times the e function unchanged. Well, the exponent is an x to the first power, so its derivative is its coefficient. Its coefficient is 1, so the derivative of the exponent is 1. So this is going to be 1 e to the x for the derivative, but I really don't need the 1, so it's just going to be e to the x. Because preceding the e to the x when there's not a coefficient, I just precede it with the derivative of the exponent. In this case, the exponent has a derivative of 1, so this is just 1 e to the x. E is its own derivative, or e to the x is its own derivative. I'm going to cross multiply, and put a plus between. So the lazy form of the derivative, y prime, equals 3x to the 4th e to the x plus 12x cubed e to the x. Let me common factor the heck out of this, one step at a time. First, between the 3 and the 12, I'm going to factor out a 3. Just so you can see the common factoring, if I was doing this by myself, I would do it in one step as opposed to the 3 that I'm about to do. When I factor out a 3, the first term turns into x to the 4th e to the x. This 12 is going to turn into a 4. Still have the x cubed e to the x. Now I'm going to factor out an x cubed. Both terms have x to the power, and the smaller exponent is 3. You factor out the smaller of the exponents. So this is going to be 3x cubed. From this x to the 4th, when I take away 3 x's, I'm left with 1x. Still haven't dealt with my e to the x's. I'll do that in a second. After the plus sign, the 4 stays. I took out the x cubed entirely, and the e to the x stays. Lastly, factor out the e to the x and get 3x cubed e to the x, and what's left is an x plus 4 inside my parentheses. That's the best answer. Usually when I have to use the product rule in these e problems or in the chain rule problems, I take the time to pull out my common factors. Let's do 11 together because it's Lee. So in 11, I don't know why I made the variable y, but I did. I'm stuck using the product rule because it's multiplication and both factors have a variable. So my first factor in 11 is y plus 3. My second or my last factor in the first factor, as I say I'm doing in number 11 and I don't, the first factor in number 11 is y plus 2. The second factor is e to the 3y. Now I'm going to find the derivative. The derivative of y plus 2 is easy. The derivative of 2 is 0. The derivative of y, because it's a first power term, is just its coefficient. There's an implied coefficient of 1. Down here, let me show the derivative of e to the 3y. It's just going to be the derivative of the exponent, because it doesn't have a coefficient. I don't need to worry about the exponent. I should write dy because the variable is y. The derivative of the exponent times the e function. 3y, the exponent has a derivative of 3. So the derivative of e to the 3y is going to be 3e to the 3y. It's just the derivative of the exponent times the e function unchanged. So this is 3e to the 3y. Cross multiply down, cross multiply up. Crazy derivative. When I cross multiply down, I don't even know which order to put it in. I'm going to put the 3e to the 3y first. It just looks better to me. But this y plus 2, it's a binomial. When I'm multiplying by it, it needs to go in a parentheses. Now I'm going to cross multiply up and get 1 times e to the 3y. That's my derivative. And I'm going to pull out a common factor of e to the 3y, because on either side of the plus sign that the product rule gives me, there's an e to the 3y. So I'm going to say the derivative is e to the 3y and then parentheses. For the first piece, I'm left with 3 times y plus 2. After the plus sign, I'm left with just a 1. I'm going to clean up this parentheses and write an answer. So this is going to be e to the 3y times 3y plus 6 to do that first multiplication plus 1. So my derivative is going to be e to the 3y times 3y plus 7. Didn't like it, but it is what it is. 13 and 14, oh, they come up a lot in our class. This is a real classic derivative for us, so you got to get this one down. Comes up a handful of times in chapter 3. It might even come up in chapter 4 as well, so it's an important derivative. When I look at 14, I see it's multiplication. Both factors have an x. So I'm going to write down the first factor, which is x, the last or the second factor, which is e to the 3x, and find their derivatives and set up for the cross-multiplying product rule. The derivative of x, since it's a first power term, it's just its coefficient. Its coefficient is 1. The derivative of e to the 3x, let me see, the derivative of e to the 3x, I could do that without coming down here. It's the derivative of the exponent, which is 3x, times the e function. The exponent just has a derivative of 3. The exponent's a first power term. The derivative of a first power term is just the coefficient. So the derivative of the e to the 3x is 3e to the 3x. Now cross multiply, put a plus between. So the derivative is x times 3e to the 3x plus 1 times e to the 3x. I'm going to pull out this common factor of 3x and write the answer in a nice order in terms of the x and the 3 that I see staring at me. So common factor e to the 3x. Before the plus sign, I have an x times 3, which I'm going to rewrite as 3 times x. After the plus sign, I'm left with a 1. That's the whole answer for 14. More grunge coming up. Got a couple of quotient rule problems. Boy, that's font. I didn't even font those up. I wonder why I didn't font them up. Yeah, I'll just deal with the lack of font. So 16 wants me to do f of t. I picked t for the variable for no special reason, just so we're not always seeing x. It's going to be a quotient rule because it's a fraction, and I can't get rid of the fraction. So I need to write denominator. In this case, it's e to the t. Numerator, in this case, it's t cubed. Derivative. Cross multiply, put a minus between, then do the denominator squared. The derivative of t cubed is just 3t squared. If I wanted to do the derivative of e to the t, it's just the derivative of the exponent. The exponent is just t times e to the t. Here, the derivative of the t, since it's a first power term, the derivative is just its coefficient of 1. And so this derivative is going to be 1e to the t, which I'm just going to write as e to the t. Now I'm going to cross multiply, put a minus between because the quotient rule has a minus, and make the denominator squared part of this as well. This is just the numerator for my quotient rule. So it's going to be e to the t times 3t squared. I probably could have written that backwards. Minus e to the t times t cubed over the denominator e to the t squared. Let me pull out some common factors. Let me first pull out a common factor of e to the t to get this dealt with. This is the easy and hard part both. Common factor of e to the t in the numerator leaves me with 3t squared minus t cubed. In the denominator, e to the t squared means e to the t times e to the t. The reason I'm attacking this e to the t first is because I knew this canceling I wanted to show right up front while I'm fresh. So I'm going to cancel those e to the t's and get the derivative is, don't need the parentheses anymore when I do this canceling, 3t squared minus t cubed over e to the t. I'm going to factor out a t squared from the numerator because both terms in the numerator have a t. And when they both have the same variable, you take the smaller exponent. So I'm going to say the derivative is t squared. To the left of the minus sign, I'm just left with a t. To the right of the minus sign, there were 3 t's. I took away 2. I'm left with 1 t. And then over e to the t. This is how I would instinctively leave my answer. If it bugs me that the t isn't written first, I can rewrite this as t squared. I can rewrite this as t squared times negative 3 plus t over e to the t. If it bugs me that that parenthesis has a negative leading it, this is where I would stop. But if it bugs me, I can factor out a negative 1, put it in front of the t squared, change the... Whoa. So I messed up here. Sorry. If I'm rewriting this, I best rewrite it with the t first and the 3 second, the negative in front of the t. So I'm running short on real estate here. But if I was going to rewrite this and not mess up, I would say this is negative t plus 3 over e to the t. So this parentheses, it's odd to see the variable written second. I can write it first. And now it's odd to see the variable lead off with a negative. I can factor out a negative 1. So I can say the derivative is negative 1 t squared. And when I factor out a negative, I flip the sign of the t. I flip the sign of the 3. I almost think this is overkill. I would leave my answer like this and be completely fine. There's not really a common factor. It's just written in a bad order. But I could write it in a good order and factor out a negative 1 if you're feeling so motivated. But I probably wouldn't do that. Even though down here, I used a program on the internet to take the derivative, and it did this for an answer. I kind of like what I have here. That's my classic by hand answer, rather than using a website to get an answer. Let's do 17 together. It's fraction, e in the denominator, a little uglier. Fraction, I need the quotient rule. So for 17, I'm going to do the denominator is e to the x. The numerator is x plus 2. I've done this once already. I'm just going to write the derivative of e to the x down without showing it. E to the x is its own derivative. We could do it off to the side, but it'll just save a second here. The numerator, the derivative of x is 1 because its derivative is its coefficient because it's a first power term. The derivative of 2 is 0, so the derivative of the numerator is just 1. Cross multiply, put a minus between. So the derivative is e to the x times 1 going down minus e to the x times x plus 2 going up over the denominator squared. Let me pull out that common factor of e to the x in the numerator and get my e to the x's attacked like I did the last problem. So pull out the common factor of e to the x. That leaves me with 1 minus, and I really need the parentheses yet for that x plus 2 in the numerator. In the denominator, I'm going to write it as e to the x times e to the x, so I can get this canceling done. When I do the canceling, I don't need the big parentheses in the numerator. I get the derivative is 1 minus parentheses x plus 2 over e to the x. Now I'm going to clear the parentheses and get f prime of x. The derivative is 1 minus x minus 2 over e to the x. And then 1 minus 2 is negative 1. This is going to be completely adequate if I wrote negative x minus 1 over e to the x for my derivative. It's written in a nice order. I combined all the like terms. The alternative would be to factor out a negative 1 from the numerator because the first term is negative. And if I factor out a negative 1, both the x and the 1 will change to positive. Both of those are good answers. These we are skipping. 19, 20, 21, 22, derivatives with bases not e in exponential functions. I'm not going to test on those. I showed them just to show you what the rules are. Just in case you ever see one of these, you can pull out the rules and do it, the derivatives, but we're not going to do those for homework. So you can skip on those 21 and 19. Now some ln's. To do the derivative of ln's, it's going to be a fraction. I don't need to think of the coefficient, but I can add the coefficient of 1 in. To do this derivative, I form a fraction. In the numerator, I write the coefficient. and then I multiply by the derivative of what's in the parentheses. What's in the parentheses is 2x. The denominator of the fraction has just what's in the parentheses. So for ln, it's coefficient. I don't really need to write the coefficient. I'll probably stop writing it. Derivative of the argument divided by the argument. So the derivative of 2x is just 2. So this is going to be 1 times 2 over 2x. And that's just 2 over 2x. And I could cancel those 2's. I can't write a fraction without a numerator. So I'm just going to write this as 1 over x. I'm going to start not writing that c. It almost seems silly to do. So let's do the c-less version because the coefficient is 1. How do I find the derivative of an ln? The derivative of an ln is a fraction. In the numerator of the fraction, it's the derivative of the argument, in this case the derivative of 3x squared. In the denominator of the fraction, it's just the argument 3x squared. The derivative of 3x squared is 6x. So an unreduced version of this derivative is going to be 6x over 3x squared. To make the canceling easier, I wrote the 3x squared with a double x. I'm going to cancel the 6 and 3. The 3 becomes a 1. The 6 becomes a 2. My x squared, which I doubled up so you can see this canceling better and see what's left, I'm going to cancel one of the x's from the x squared with the x from the derivative in the numerator and be left with an x in the denominator. So what I'm left with in the numerator is 2. What I'm left with in the denominator is x. The derivative of 26 is just 2 over x. Once I start seeing adding or subtracting in the argument, the derivative's not going to reduce. So for 28, the coefficient is 1, don't need to worry about it. The derivative is the derivative of the argument in the numerator of the fraction divided by the argument in the denominator of the fraction. Once there's a plus or minus in the denominator, you can only cancel with an identical factor. It has to be straight multiplication to do the kind of reducing I've been doing. This derivative, the derivative of 5x is 5, the derivative of minus 2 is 0, so that derivative is just 5. And a 5 can't cancel out the 5 and the 5x minus 2. If it was 5x times 2, if that minus was a times, it would be allowed to simplify the 5. Because it's not, I can't. Oh, here we go to the product rule. So 30, I need to use the product rule because it's multiplication, but both factors have an x. So for 30, I want my first factor of 8x and my second or my last factor of the natural log of 9x. I'm going to take the derivative here of 8x. The derivative of 8x is just 8. For the derivative of the natural log of 9x, I get a fraction, and the numerator of that fraction is the derivative of 9x, and the denominator of that fraction, I don't know why I just put a parentheses, is the argument of 9x. So the derivative of 9x is just 9, and then the denominator doesn't change. With straight multiplication, I can reduce. These 9's are going to reduce to 1's, and I'm going to get the derivative is 1 over x. So beneath the natural log of 9x, I'll put a 1 over x. Cross multiply, put a plus between. So the derivative is 8x times 1 over x plus 8 times the natural log of 9x. Cancel these x's and get something that's suitable for an answer unless I want to pull out a common factor of 8, which is fine. And if I want the x term written first, also fine. This is an okay answer. I can go a couple different ways. I can pull out a common factor of an 8. This 8, if I pull out an 8, it will turn to a 1. That 8 will turn to a 1 and leave me with the natural log of 9x. Equally good answer. And if it bugs you that the 9x, the natural log, the x piece is written second, you can also do this. all of those acceptable answers. Let's do 31 together. It's a product rule because it's multiplication and both factors have a variable y. So for 31, immediately I see product rule. The first is a y squared. The second or the last is the ln of 3y. It's multiplication. Both factors have a y. I need the product rule. Can't even spell derivative. The derivative of y squared is 2y. For the derivative of the natural log of 3y, I form a fraction. In the numerator of the fraction, I write the derivative of 3y. In the denominator of the fraction, I get that whole 3y. The derivative of 3y is just the coefficient 3. The denominator stays 3y. Since it's straight multiplication in the denominator, I can cancel the 3's and get 1 over y for its derivative. Now cross multiply, put a plus between to finish up my product rule. So f prime of y equals to y squared times 1 over y plus 2y times the natural log of 3y. That's just cross multiplying both directions, putting a plus sign between. This y squared will cancel with this y. The y will go completely away. I'll lose one of the y squareds and just be left with a y. So this canceling gives me y times 1, which is y, plus 2y, natural log of 3y. You can't add this and get a 3y. Those aren't like terms, but I can factor out a y and say the derivative is y, the common factor, then 1 plus 2 times the natural log of 3y. That's probably where I would leave my work, but you certainly can rewrite the problem with the natural log of 3y piece first in the 1 second. Not going to be responsible for logs base anything but ln, so we're going to skip 33, 34. We're going to skip 35, 36. And as much as I don't want to, this is yeah, well, no, there's only a few problems. Let's make this a 36-minute video and not have a part 3. So this is repetitive. We've been doing horizontal tangent lines. This is the 3rd time they've come up. And let me do, there's 4 problems. Let me do the harder one of the 4. Let me do problem 39 with you. And then see what the timer is like, and if it's good, I'll go back and do 42. But the instructions are going to be the same. So when I ask you to find all values of x where the tangent line is horizontal, so for 39a, I'm going to find the derivative, set it equal to 0, and solve for x. This has a trick that comes up a lot in our class that you may or may not have been exposed to. It has to do with e to a power equals 0 never having a solution. So let me do the derivative. First factor is 3x. Second factor is e to the x. I'm setting up for the power rule because both factors have x's. The derivative of 3x is just 3, and we did this before. The derivative of e to the x is just e to the x. Cross multiply, cross multiply. The derivative is going to be 3x e to the x plus 3e to the x. Let me factor out both a 3 and an e to the x just to be efficient. I'm going to get y prime is 3 e to the x. I took that 3 and that e to the x away from there, so from the first piece I'm just left with an x. After the plus sign, I've taken away the entire identical factor, so I leave a 1 behind. So I found the derivative. Now I'm going to set it equal to 0. And it turns out that e to some power can never be 0. If you plug in positive numbers, you get huge numbers. If you plug in negative numbers, you get fractions. There's no way to get 0 when you set e to some power. So now that I have it factored, I set the factors equal to 0. And e to some power, or a constant times e to some power, can never be 0. There's no number I can plug in. If I plug in 0, I get 1 for the e. If I plug in a negative number, I get a fraction. There's no way to turn that piece 0. But the x plus 1, I can certainly get 0 by just minusing 1 from both sides. The answer to 39a is going to be x equal to negative 1. That's the value of x where the tangent line is horizontal, which means the slope is 0. Moving on to 39b, I need to have a point, which is x coordinate is negative 1. I don't know its y coordinate. And I need to know the slope. The slope is 0 because all horizontal lines have slopes of 0. So we're at the place where we've been a couple times. I just need to find the y coordinate of the point. To get the y coordinate of the point, I'm going to go to the function 3x e to the x and plug in negative 1 for x. So I'm going to go 3 times negative 1 e to the negative 1. This is going to give me y equals negative 3 e to the negative 1. That's going to give me y equals negative 3 over e to the first when I go to make that exponent positive. So my y coordinate of my point is negative 3 over e. I get the y coordinate by plugging in 0, or plugging in the x value into the original function. Now I do y minus the y coordinate equals the slope. Horizontal lines have a slope of 0 times x minus the x coordinate. The left-hand side, the double negative, I could make positive. And the right-hand side, 0 times anything is 0. Now I'll just minus 3 over e from both sides. You might start seeing a pattern. The answers to the equations of the tangent lines, when they have horizontal lines, it's always y equal the y coordinate of the point. Horizontal lines only have y's in their equations and not x's. And the y coordinate of the point will do that just fine. Let us do 37. I'll do 38 and leave you 37, and then we'll stop the video. So for 38, same instructions. Find the values of x where the tangent line is horizontal. So for 38a, I need to find the derivative, set equal to 0, and solve for x. That's anytime I'm asked to find the values of x where the tangent line is horizontal. It's always find the derivative, set it equal to 0, solve for x. Well, the function is e to the 5x squared. I know its derivative is just going to be the derivative of its exponent times the e function unchanged. It doesn't have a coefficient to worry about. So the derivative of the exponent is 10x, and then the e function unchanged is just the 5x squared. So the derivative of the function in 38 is 10x. The derivative of 5x squared is 10x. It's 10x e to the 5x squared. So this is the finding the derivative part of finding the values of x where the tangent line is horizontal. Then I take the derivative, set it equal to 0. The derivative is factored, so I split the factors apart and set each factor separately equal to 0. For the 10x, I divide by 10 and divide by 10 and get x equal to 0. And an e function can never be 0. There's never going to be a solution there. So my answer to 38a, the value of x where the tangent line is horizontal, is x equal to 0. Now I'll move on to problem B of 38. And for part B, I have the x coordinate of a point, which is 0. I have the slope, which is 0 because horizontal lines have 0 slopes. Now I need to get the y coordinate of the point by plugging in 0 for the x. So my y, going off screen now, my y is going to be e to the 5 times 0 squared power. I take the value of x from part A, plug it into the x into the function. This is going to give me y equals e to the 5 times 0 power. This gives me y equals e to the 0 power, and I know that that's equal to 1. So now I have slope and a point, and I can just go y minus the y coordinate of the point equals the slope times x minus the x coordinate of the point, 0. That mistake was forgivable because the right side's going to come out to 0 because 0 times anything is 0. Now I'm going to add 1 to both sides and get y equal to 1 for my answer to 38b. There is a problem 41 and 42 that you can make a stab at. It's very similar to problems 39 and 40 that I did, so you can give these a crack. Hopefully this didn't feel humbling. E derivatives and Ln derivatives, they're really not that bad. And even the algebra, it's not as bad as some of the algebra that we've seen, especially in the first chapter. So we just have one section left before we get to the practice test and the test.